Greetings, mathophiles. Welcome to the second in a series of 3 videos introducing the concept from calculus of the definite integral. The first video was an introduction to what are called Riemann sums and how they can be used to begin to address the area problem. This video will look at a formal definition of the limit and then take a look at a couple of examples that have to do with that formal definition. And then the third and final video will involve properties of the definite integral. There's also going to be a moment in this video where we're going to employ a couple of summation formulas that you likely will have encountered previously, but that you might not remember. The first is that the sum of the first n integers is n times quantity n plus 1 all over 2. And the second is that the sum of the first n squares of the integers is n quantity n plus 1, quantity 2n plus 1 all over 6. To quickly recap the introduction from the first video, our goal was to take a look at the area of the region bounded by the lines x equals 2 and x equals 5, the x-axis, and the function f of x equals x plus x squared. And the approach that we took was to chop that interval, closed interval 2, 5, into a number of subintervals of equal width. Each of those subintervals becomes the base of a rectangle. The height of the rectangle becomes the value of the function somewhere on that subinterval. And typically one uses either a left endpoint, a right endpoint, or a midpoint of the subinterval as a way of locating the value that you're going to plug in to define the height. This happens to be a picture using left endpoints. We can switch that picture to midpoints. We can switch that picture to right endpoints. Just as an aside, it quickly becomes apparent that if the function is increasing on the interval, the right endpoint estimate is going to be high, the left endpoint estimate is going to be low. Should surprise no one that those roles are reversed for a decreasing function. And what we observed was that the more of these subintervals you have, the more narrow they are, the better the job you seem to do of approximating the region with the sum of the area rectangles. And that pointed us at the end of the first video in the direction of taking the limit of the sum of those areas. And so that's what we're going to do. We should note, by the way, that functions get to be negative. And if you recall the formula for the Riemann sum, we took these function values as the heights. If the function's negative on a subinterval, then the function value is going to be negative, and the area of that rectangle is going to make a negative contribution to the sum. And it turns out that that's okay. So start preparing your brain for the notion of negative area because it's going to come up as we get more deeply into the process of integration. You'll see on your screen the definition that I've chosen to use for this video of the definite integral. And that swoopy thing is called an integral sign. And that first piece of the definition is read, the integral from a to b of f of x dx. A is called the lower limit of integration. B is called the upper limit of integration. The function is called the integrand, the function that's being integrated. And then the dx is a piece of notation that signals to us unambiguously what the variable of integration is, what the independent variable is. Similar role to the ddx in the derivative operator notation. So if our independent variable were t, that would be a dt. If it were w, it would be a dw, whatever. It tells us what the variable of integration is. Pretty important now, and uber important for those of you who end up taking multivariable calculus. And that's said to be equal to the limit as n approaches infinity of the sum k1 to n of f of x sub k star delta x. In other words, the limit of a Riemann sum. The limit, if you think of it graphically, of the sum of a bunch of rectangles of a bunch of areas on the interval. This is called the definite integral of f on closed AB, where delta x is b minus a all over n, and x sub k star lies somewhere on the kth subinterval. So somewhere between x sub k minus 1 and x sub k. When you're differentiating, in situations where the limit that defines the derivative doesn't exist, we say that the function is not differentiable. And when the limit does exist, we say the function is differentiable. There's an analogous concept with integration. If the limit in this definition does not exist, we say the function is not integrable on the interval. And if it does exist, we say the function is integrable. And there are a few things we should say about integrability. There's a lot more, certainly, that's there, but this will get us going for the next little while. First, and critically and usefully, if a function is continuous on a closed interval, then it is integrable on that closed interval. That's a direct consequence of the fundamental theorem of calculus, and many of you will encounter that pretty soon if you're sort of viewing these videos in a typical order. It's also true that if a function is unbounded on an interval, then it is not integrable, which means, among other things, that vertical asymptotes are deal breakers. And finally, if a function has only a finite number of discontinuities and is bounded on an interval, then it's integrable on that interval. And all it means for it to be bounded is there's some number above which it can't go and some number below which its value can't go on that interval. We're going to look at 3 examples. And the first one goes directly to one's understanding of the structure of this definition. And it's of a type that is beloved of AP Calculus exam question writers. The second example will basically be an instance of sort of doing the first one in reverse. And then finally, we'll go through a full-blown derivation of the value of a definite integral, and then we'll sort of check it numerically. So, first example, write the integral that you see here as a limit of a Riemann sum. In other words, re-express it using the correspondence that you see in the integral definition. And it's the integral from 1 to 9 of the square root of x dx. So if we're going to write it as a limit of a Riemann sum, we need to know what the delta x's are going to be. The widths of the subintervals. Well, the entire interval is 8 units wide, right? It runs from 1 to 9. So 9 minus 1 divided by the number of subintervals, which is n. So delta x is going to be 8 over n. Then we need to know what the x sub k stars are. And we have some choices. We can use left endpoints, we can use right endpoints, we can use midpoints. The right endpoint is the play that I always choose if I'm given the option to choose, because it's the one that is the least complicated algebraically. And to get to a right endpoint of one of these subintervals, I just start at 1, which is the left edge of the entire interval, and I go the right number of delta x's. And the right number of delta x's to get to the right endpoint is k. And if you'd like a review of how this works, you can certainly go back to the first video where we unpack it in quite a bit more detail. So my delta x again was 8 over n. So I can write this slightly more compactly as 1 plus 8k over n. Now I just need to put things where they go. This thing will be the limit, n to infinity, sum k1 to n, f, which is a square root function of x sub k star times delta x. Typically not so bad if you know how to get the delta x, and if you know how to get any of the various typically used x sub k stars. There you go. This is not that difficult. Here is our second example, and it essentially reverses the process that we were asked to use in the first example. So we are to write this limit of a Riemann sum as an integral. It's a limit n to infinity, sum k1 to n of the thing that you see in front of you. This is a little trickier task than the one we just completed, because you have to sort of tease apart from this expression what is the delta x, what is the x sub k star, and what is the f. And occasionally there are situations where you have a constant factor floating around, for example, where you could maybe conceive of it in more than one way. But let's see if we can pick this thing apart and do a decent job of re-expressing it. It is not a certainty, but it is a decent bet that this thing hanging off to the right is delta x. So let's imagine provisionally that delta x is pi over n. So if that's being the case, then this pi over n becomes a delta x, this pi over n becomes a delta x. And if that were the case, then these two terms here would be k delta x. And if you'll recall, your x sub k stars are a plus some constant times delta x, and that constant's either k or k minus 1 or k minus a half in the civilized world. So it's a decent bet that that is k delta x, which means it's a decent bet that that's a. So let's imagine that x sub k star is pi over 2, which is a, plus k times pi over n being delta x. Then this thing would be an x sub k star. This thing would be an x sub k star. And so it would seem that our f is x plus sine x. And it works out, right? Here's an x sub k star here plus a sine of x sub k star times the delta x. So I think we've got all these things appropriately identified. So this is going to be the integral of x plus sine x dx. Now, what are my limits of integration? My lower limit of integration should be my a. It should be pi over 2. My upper limit should be my a, which we just said was pi over 2, plus n of these delta x's, right? Delta x is supposed to be 1/n of the way from a to b. So if I know what delta x is, I multiply it by n. I've got the difference between a and b. So this is going to be n times pi over n, which means it's pi over 2 plus pi, which is 3 pi over 2. If you have doubts about that, and you may because it's a more complicated process, you could then take this thing and break it apart and try to re-express it as a limit of a sum and assure yourself that we in fact did it correctly. Our final example is a bit of a slog, and my feelings won't be hurt if you give it a miss. What we're going to do is to work out a definite integral using the definition and then evaluate the resulting limit of the Riemann sum. And it's a thing that your instructors may not be asking of you, but I think it's good to see at least one of these so that you, if nothing else, develop some real appreciation for the methods that we're going to be employing more regularly. So you'll see back on the screen our function, which again was f of x equals x plus x squared. It's on closed to 5, and we're looking at right endpoints. And if I seriously increase the number of subintervals to the point where we have 100 of them, the sum of those rectangle areas is about 49.9, okay? If I switch to midpoints, it's about 49.5. If I switch to left endpoints, it's about 49.1. You probably can't really see on the screen much difference, but I did switch them. So it would seem to be the case that this integral, if it truly represents this area, is going to have to be somewhere in the neighborhood of 49 or 50. It's reassuring that they're all pretty much in the same neighborhood as one another. And so let's go to the document camera and let's pound this limit out in the hope and expectation that it lands somewhere in the neighborhood of 49 or 50. So you see under the document camera the integral that we intend to evaluate. It's the integral from 2 to 5 of x plus x squared dx. And it should be the integral that corresponds to the area that we were looking at on the Desmo screen. So before we begin, or as we begin, we need a delta x. That's going to be the width of the interval, which is 3, since it runs from 2 to 5, divided by n. And we need an x sub k star. And the way we get to a given x on the kth subinterval is to start at a, which is 2, and go the right number of delta x's. So what's the right number of delta x's? Well, if it's left endpoints, it's k minus 1. If it's midpoints, it's k minus a half. If it's right endpoints, it's k. And algebraically, right endpoints are then going to be more convenient. So we certainly want to consult our convenience whenever possible. So k delta x is going to be k times 3 over n, or 3k over n. So our integral is limit n big sum k1 to n f of x sub k star. So basically, I take this expression x plus x squared. Wherever I saw an x, I stick in our expression for x sub k star, and then finally we got to multiply by the delta x. So this will be 2 plus 3k over n plus the square of 2 plus 3k over n, all times the delta x, which is 3 over n. And if that looks a little bit annoying algebraically, I'm with you, but we should be able to pound our way through to a real number. If what I said earlier was true about continuous functions having being integrable, having values for their definite integrals, then it's our own fault if we can't get to a result. So next, I believe we'll square the binomial. So sum k1 to n, limit of that sum, 2 plus 3k over n plus 4 plus 12k over n plus 9k squared over n squared, all times 3 over n. If I'm doing the algebra a little quickly, if I'm doing what seem to you to be too many steps at once, just pause the video and throw in another step or two and verify for yourself that what we're doing is correct. Next, I'm going to collect like terms and distribute the 3 over n. So this is limit n big sum k1 to n. Do I have to keep writing the lim and the sigma? Yes. If they're not there, then what you're writing is not true. It's not that the limit of the sum of this thing is equal to just this thing. It's equal to the limit of the sum of the next thing and the limit of the sum of the next thing and so on. So if it's not there, it's not sense. And we want to always make sense whenever possible. There are times when it doesn't feel possible. So when we can, we need to do it. So 2 plus 4 is 6. Distribute the 3 over n, 18 over n. 3k over n plus 12k over n is 15k over n, times the 3 over n is 45k over n squared. And finally, we have this last term here, so multiplied by 3 over n, we get 27k squared over n cubed. It looks a little nicer. Next, let's distribute the sigmas across the 3 terms, which is a legit maneuver in the world of summation notation. So this is limit n big sum of 18 over n plus sum 45k over n squared plus sum 27k squared over n cubed. And these sums are all as k goes from 1 to n. Now, oops, close the parentheses. Now I can factor out any common factor in the, doesn't have to be common. I can take out any factor in any one of these sigmas that doesn't depend on k. So, now let's go back up to the top so we leave room for the captions. This is limit n huge sum. Well, the entire 18 over n can come out, right? It doesn't depend on k at all. So I have 18 over n sum k1 to n of whatever's left over after that division. It's just 1. Then I can pull out in the second sum the 45 over n squared, leaving me with the sum of the k's, k1 to n. And finally, in the third sum, I can pull out the 27 over n cubed, leaving the sum of the k squares, k from 1 to n. All right. Limit n huge. If I add up n ones, I get n. And 18n over n is 18. Feels like progress. Next term, we've got the 45 over n squared. And now we tried out one of those summation formulas that I flashed on the screen right at the start of the video. The sum k1 to n of k is n times n plus 1 all over 2. Then we have 27 over n cubed. Sum of the k squares is n times n plus 1 times 2n plus 1 all over 6. Now, the limit as n goes to infinity of 18 is, wait for it, 18. What about that second term? These other two terms are rational expressions. Their values are going to be driven, since it's a limit n to infinity, their values are going to be driven by the highest degree terms. Highest degree term above is 45 times n, or 45n squared. Below we have a 2n squared, and so that's going to 45 halves. And finally, highest degree term on top, we got 27, we got n, and 2n, so 54n cubed over 6n cubed, that's going to 9 as n gets huge, and the lower degree terms are drowned out. And if I add these up, I get 49.5, which should be deeply reassuring given what we've seen thus far numerically. For those of you who made it to the end of the third example, bravo. And for you and for those who skipped to the end just to hear me say it, happy mathing.